The rest of this section is really applications of exponential functions. And the first application we're going to look at is actually fairly important. We're going to focus on cases where we talk about exponential growth and decay. And these situations actually pop up all over the place. But exponential growth, you're going to primarily see when you are in a context where there might be plentiful resources and or no limits or restrictions on that population or quantity that you're working with. Okay, so think of this as like if you put, say, all your money in the bank and it just grew at whatever rate it wanted to, and without any restrictions, you had like a great interest rate. This is the sort of situation you'd be in. Okay, typically it doesn't match in reality, but it can be a good model at least to get a feel for what could happen. Okay, so when we work with an exponential growth model, the base equation, okay, so we typically begin with like y equals b to the x, and then we're just going to scale this. Okay, in exponential growth models, we actually let things vary just a little bit. In these contexts, we let b equal e to the r, okay? And then in that case, we'd have a e r to the x, oops, okay? And in this situation, if we have exponent to exponent, we would end up multiplying the exponents. It'd be a e to the rx. Okay, typically, instead of t, we're working with time, or instead of x, we're working with time, so we typically let x be t. And then the other interesting thing is that this a, we typically use a subscript of a0 on it to indicate some initial amount, a0e to the rt, okay? So if you want to make some notes, a0 would be like the initial amount, and then r is, there's not great language around it, but we can just say it's going to be a growth constant. Okay, I don't want to use the term rate, but it could be a growth constant. Okay, so an example of this we could see similar into that very opening example from this section of instruction, talking about bacteria in a colony, and at least for a very short time. And if we have a sufficiently large space for them to grow, they can grow according to an exponential model. And in fact, that model is given here. Okay, so questions are, how many bacteria were there initially? And I'm going to say there were 300. How did I get that? Well, 3, if I look at this, 3 is a0, and the r is 1.2. Okay, so then I just say initially there were 3, but then I'm saying in hundreds, right? So I just 300 bacteria. B, by what percentage did the colony grow from day 1 to day 2? So, okay, I mean, if I want to do this out hardcore, I'll say 1. If I calculate that, that would be 3e to the 1.2. And so if you put that into a calculator, you get this 9.96 approximation number. Okay, and then if you put day 2 in there, so it'd be 3e to the 1.2 times 2, right? 2 for t, you would get 2.4 there. And then if you put that into your calculator, you get approximately 33.069. And then by what percentage did the colony grow? Okay, so then you do like n of 2, so the final minus the previous, or the current times the previous, or divided by the previous. And if you do that, let's see, putting that in my calculator, I get, let's see, and I'm going to be as precise as I can with my approximation. I get 3.32. Okay, so as a percentage, that'd be 332%. Okay, about. Okay, coincidentally, this 3.32 number is e to the 1.2. Huh, that's interesting. And then if you want to generate the graph and then look at the long-term behavior, you sure can, but in C, it says comment on the long-term behavior of the colony. Well, what do we know? We know B is this e to the 1.2, the 3.32 number, and that's greater than 1. So then that would mean that as time gets arbitrarily large, the number of bacteria in the population should also go to infinity. Okay, you can look at a graph most certainly, put it into Desmos with using y and x, and you get the graph. Okay, so that's exponential growth. The other scenario is kind of the flip side, where we have decay or decreasing, right? And so that's just where you have very limited or no resources or interventions to prevent depletion. Okay, and in the same vein, we would begin with saying, okay, our base amount is A, and then B to the X, and typically, again, we have time, and then in these scenarios, we let B equal e to the R, and we also let A equal A0, so then we get the same sort of thing. E R to the T, or Y is equal to A naught e to the RT. And so the real question is, how do you know if you have growth or decay, right? They're the same equation. Depends on the value of B, right? In growth, we had a B value greater than 1. As we work with decay, B is going to be between 0 and 1, okay? So that's how you know the difference. Now, also there's another little bit of terminology that we need to be aware of. We'll do more with it going forward, but half-life, it's just the amount of time. Again, it is the amount of time that we need for 50% of the quantity to be depleted if you're a glass half empty person, or if you're a glass half full person, to be 50% of the quantity to remain. Okay, because we begin at 100% of it and then it slowly fades away, right? So if mathematically, what we will see, we'll solve this more precisely later on. Okay, so if you begin with this amount, this base equation, A naught e to the RT, well, now we're saying that y is equal to half of what we began with, right? So take A naught divided by 2. A naught divided by 2 is equal to A naught e to the RT. Divide both sides. Divide by A naught. And we get 1/2 is equal to e to the RT. And typically in these scenarios, if you're looking for half-life, right, that means you're going to have to find what t is. Now, how do you do that precisely? I'm just going to say more on this later. We will solve this more precisely. But to do this, we need to get the unknown out of the exponent, which requires an inverse function. So we'll see that coming up. Okay. So cesium-137, it's a radioactive material, and so radioactive materials decay over time, right? A half-life of 30 years. So we're going to use a computer algebra system, aka Wolfram Alpha, to help us solve and figure out this decay constant K, or if we want to use, instead of K, we can use R, same sort of thing. And then we want to write an exponential function for a 2-gram sample of cesium-137. Okay, so before I go any further, what I'm going to be writing is going to look like y is equal to A naught e to the RT, and in this, I already know what A naught is, 2 gram, right? E, and then I need a number, and then T. Okay, so I just need to figure out what that number is. Okay, so that's what I want. Okay. Now, what do I actually need to put in a computer algebra system, or what do I need to use in Wolfram Alpha? Okay, that's where this half-life equation comes into play. E to the RT, okay? And specifically, I want to know what R is if T is 30. So I'm going to tell Wolfram Alpha to solve that. So here's Wolfram Alpha, and I need to tell it to solve 1/2 is equal to e to the power of x times 30. Or I'll just say 30x. And then this should be enough. And there is an expression for it if we get an approximate answer. Okay, so it's like negative 0.023. Okay, let's use that. R is equal to negative 0.0231. Negative 0.0231. Okay, there we go. Okay. And again, negative exponents, we could make it positive by instead, if we wanted to, we could do this like 2 times 1 over e to the positive 0.0231 times t. Okay, that could work as well. Okay, you don't have to. But then part B, now this is just saying when t is 30, t is 60, and when t is 100. Okay, now I'm going to omit the exact calculations. Well, I'll just kind of write down the answers that I get. But we are substituting 30, 60, and 100 in for t, and what we should see is as we look at these amounts, so as we calculate the y values, the amounts should be decreasing because there's less of this stuff remaining, right? We're decaying over time. So that's what we should see. Here are my answers. So 30 was a half-life, right? So if we began with 2, right, 50% of it's gone, so 1 remains. 50% of 2 is 1, right? And then 60 is another half-life. It's a quarter life, actually. But it'd be half of the half remains, so half of 1 remains, so 0.5. You can actually get that with a calculator too. But now for this one, you actually had to use the model. You had to put in 100, and I got out about 0.2. So 0.2 grams remains after 100 years. So getting closer to 0, but never actually equaling 0. So as you look at using exponential functions, you will likely encounter situations where you come into contact with exponential growth and decay. And so again, you have the same model in each one. It's just a matter of figuring out, okay, are your values increasing or decreasing over time? And so applying these ideas as needed to get the right model.